Hello there, and welcome to the Scientist Sleepy. Tonight, we embark on a gentle, quiet exploration into a question that whispers at the edges of our consciousness. Why is life, as we know it, found only here on our precious Earth? We will drift through the solar system, a slow, cinematic journey examining the profound, and sometimes surprisingly simple, reasons why our neighboring worlds remain inhospitable. This is not a race for answers, but a serene contemplation of the extraordinary circumstances that have allowed life to bloom on this one, blue marble. Prepare to let go, to be curious, and to find a deep, quiet wonder as we uncover the unique tapestry of our home planet. Let us begin our drift. The Earth is a miraculous anomaly. Our solar system, a beautiful, orderly dance of celestial bodies, is a singular stage upon which life, as we understand it, has found its only known home. While we gaze out at the vastness of space, at the myriad stars and the planets that may orbit them, it is here, on this small blue marble, that the intricate, improbable symphony of existence plays out. Earth is not merely a planet. It is a testament to a precise confluence of factors, a delicate balance that, upon closer inspection, reveals itself to be nothing short of miraculous. Consider, for a moment, the sheer audacity of our existence. We are born from stardust, our very atoms forged in the hearts of long-dead stars, now gathered here to contemplate the universe that birthed us. This is not a given. For life to arise and thrive, a complex interplay of cosmic and terrestrial conditions must align. Earth possesses a unique combination of attributes that, when considered together, paint a picture of extraordinary fortune. Firstly, our planet's distance from the Sun is remarkably precise. We reside within what astronomers call the habitable zone, or the Goldilocks zone, not too hot, not too cold, but just right for liquid water to exist on our surface. Too close, and our oceans would boil away into a steamy, uninhabitable atmosphere, much like Venus. Too far, and our waters would freeze into an impenetrable layer of ice, rendering life as we know it impossible, a fate similar to that of Mars. This orbital sweet spot is a narrow band, and Earth has maintained its position within it for billions of years, a feat in itself given the gravitational tugs and nudges of other planets. This stability has allowed for the gradual, unhurried evolution of life, from the simplest single-celled organisms to the complex tapestry of biodiversity we see today. Beyond mere distance, Earth's atmosphere plays a crucial role. It is a finely tuned shield, composed primarily of nitrogen and oxygen, with trace amounts of other gases. This atmosphere protects us from the harsh vacuum of space, shields us from most harmful solar and cosmic radiation, and regulates our temperature through the greenhouse effect. Without this atmospheric blanket, the temperature swings on Earth would be as extreme as those on Mercury, ranging from scorching hot during the day to freezing cold at night. Furthermore, our atmosphere provides the very air we breathe, the oxygen that fuels our metabolism. The presence of a substantial, stable atmosphere is not a common occurrence. Many planets and moons are either too small to retain one, or too close to a star to prevent it from being stripped away by stellar winds. Then there is the presence of abundant liquid water. Water is the universal solvent, the medium in which the complex chemical reactions that underpin life occur. It transports nutrients, regulates temperature, and is an integral component of every living cell. Earth's abundant oceans, lakes, and rivers are a direct consequence of its temperature and atmospheric pressure, creating a hydrosphere that is essential for life's genesis and sustenance. The journey of water to Earth, whether delivered by comets and asteroids in the early solar system or outgassed from the planet's interior, is a story in itself. but its enduring presence is an undeniable cornerstone of our planet's habitability. Our planet's magnetic field is another vital, often overlooked, anomaly. Generated by the molten iron core spinning within Earth, this magnetic field extends far into space, creating a protective bubble known as the magnetosphere. This invisible shield deflects the stream of charged particles emanating from the sun, known as the solar wind. Without this magnetic protection, the solar wind would gradually strip away our atmosphere, leaving the surface exposed to damaging radiation. Planets like Mars, which lost its global magnetic field billions of years ago, show clear evidence of atmospheric erosion, a stark warning of what can happen when this vital shield weakens. Furthermore, Earth's geological activity, particularly plate tectonics, has been instrumental in fostering and sustaining life. The slow, constant movement of Earth's tectonic plates recycles essential elements, regulates atmospheric composition through volcanic outgassing, and creates diverse environments that drive evolution. Volcanic activity, while sometimes destructive, releases gases that replenish our atmosphere and oceans, and the formation of continents and ocean basins has created a dynamic planet with a rich variety of ecological niches. This geological dynamism, a hallmark of a geologically active planet, is a rarity in the cosmos. Finally, the sheer longevity of these conditions is remarkable. For billions of years, Earth has maintained a relatively stable environment, allowing life not just to arise, but to evolve and diversify into the myriad forms we see today. This prolonged period of stability, free from catastrophic asteroid impacts that could sterilize the planet or drastic climate shifts, is crucial for the complex, multi-stage process of biological evolution. In the grand, silent theater of the cosmos, Earth stands out not as just another speck of dust, but as a rare jewel, a place where the improbable has become profoundly real. And so, this unique convergence of distance, atmosphere, water, magnetic field, geological activity, and time allows this vibrant, breathing world to be our home, a gentle reminder that our existence here is a profound and precious gift. Venus is a hellscape of unyielding heat. Imagine a world perpetually shrouded, a canvas of swirling, acidic clouds that reflect the sun's light with an almost blinding intensity. This is Venus, our closest planetary neighbor, a place that, at first glance, might seem like a twin to Earth, but whose reality is far more extreme. The surface temperature of Venus averages a staggering 462 degrees Celsius, or 864 degrees Fahrenheit. To put that into perspective, that's hotter than the melting point of lead, hot enough to vaporize most common metals. This inferno is not a transient phenomenon. It is the constant, unyielding state of Venus's surface. The primary culprit behind this extreme heat is a runaway greenhouse effect, a consequence of Venus's incredibly dense atmosphere. Composed overwhelmingly of carbon dioxide, about 96.5%, this thick blanket traps solar radiation with an efficiency that Earth's atmosphere, while also a greenhouse, can only dream of. Even though Venus is farther from the sun than Mercury, its thick atmosphere makes it hotter. Mercury, despite its proximity to the sun, has virtually no atmosphere to retain heat, leading to dramatic temperature swings between its sunlit and shadowed sides. Venus, on the other hand, is a uniformly baked oven. The atmospheric pressure at the surface of Venus is also immense, about 92 times greater than Earth's atmospheric pressure at sea level. This is equivalent to the pressure experienced at a depth of nearly 1 kilometer, 0.6 miles, in Earth's oceans. Imagine the crushing weight of that atmosphere bearing down, a force so great it would instantly flatten any terrestrial structure. The clouds themselves are not made of water vapor, as they are on Earth, but of sulfuric acid. These highly corrosive droplets descend from the upper atmosphere, creating a perpetual, acidic rain that never reaches the surface, instead evaporating in the intense heat miles above. This chemical composition, combined with the extreme temperatures and pressures, makes Venus an environment utterly inhospitable to life as we know it. There is no liquid water on the surface, no respite from the searing heat, and no protection from the corrosive atmospheric soup. The very air we breathe would be a deadly poison, and the ground beneath our feet would be a molten inferno. The geological activity on Venus is also a subject of intense study. While we don't observe active plate tectonics like on Earth, radar mapping has revealed vast plains, massive volcanoes, and evidence of significant volcanic resurfacing events. These events likely contribute to the continuous release of greenhouse gases, perpetuating the planet's thermal equilibrium. The extreme conditions on Venus serve as a stark reminder of how delicate the balance of planetary conditions must be to foster and sustain life. It is a world that showcases the potential for a planet's atmosphere to become a suffocating shroud, transforming a potentially habitable world into a cosmic crucible. The lessons learned from Venus highlight the critical role of atmospheric composition, density, and the presence of liquid water in determining a planet's habitability. It is a world of intense beauty in its swirling cloud formations, yet a place of profound hostility, a testament to the diverse and often extreme outcomes of planetary evolution in our solar system. The sheer power of the greenhouse effect, amplified to such a degree, is a humbling scientific spectacle. It is a world where the very fabric of existence is forged in fire and pressure, a stark contrast to the gentle embrace of our own home. The unyielding heat of Venus is a constant, silent testament to the precarious nature of life's foothold. Even in its fiery embrace, Venus whispers a profound truth about the preciousness of our own world's gentle warmth. Mercury offers no protection from cosmic fury. Imagine a world so close to the sun that its surface is perpetually bathed in an intense, searing radiation. This is Mercury, the innermost planet of our solar system. Its proximity to our star means it receives an overwhelming dose of solar energy, a relentless bombardment that would be utterly destructive to any complex life as we know it. But the fury isn't just from the sun's direct heat and light. Mercury also faces the constant barrage of charged particles, known as the solar wind, and cosmic rays originating from distant, violent celestial events. Unlike Earth, which is shielded by its robust magnetic field and a substantial atmosphere, Mercury possesses neither. Its magnetic field is incredibly weak, a mere whisper compared to Earth's protective embrace. This feeble field offers virtually no defense against the energetic particles streaming from the sun, which can strip away any atmosphere that might try to form and bombard the surface with damaging radiation. Furthermore, Mercury has an atmosphere so tenuous, so thin, it's often referred to as an exosphere. This wispy layer is composed of atoms that have been sputtered off the surface by solar wind and micrometeoroid impacts. It's so incredibly thin that it provides no significant barrier against the incoming cosmic radiation or the solar wind. Any molecules that might exist there are quickly lost to space. Without this atmospheric blanket, the surface of Mercury is directly exposed to the harsh realities of space. The solar wind, a stream of plasma continuously flowing outward from the sun, impacts Mercury's surface with considerable force. This interaction can erode the surface over eons, and more importantly, it means that any potential for a stable, life-supporting environment is immediately compromised. Cosmic rays, high-energy particles originating from supernovae and other energetic astrophysical phenomena, also travel unimpeded to Mercury's surface. These particles are highly ionizing and can damage DNA and other complex organic molecules. On Earth, our atmosphere and magnetic field deflect the vast majority of these harmful rays, allowing life to flourish in relative safety. On Mercury, however, there is no such buffer. The planet's surface is a stark, exposed landscape, constantly under siege from the very forces that power our own solar system, but without any of the mitigating factors that make Earth a haven. The lack of a significant magnetic field means that even the solar wind, which on Earth causes auroras and can be a hazard to satellites, directly bombards Mercury's surface, stripping away any volatile materials and contributing to the erosion of its landscape. This constant exposure to high-energy particles and intense solar radiation creates an environment that is profoundly hostile to the delicate chemistry of life. The very forces that sustain our planet's warmth and light become instruments of destruction on Mercury, a stark reminder of the fine balance required for life to take hold. On this stark, exposed world, the sun's fury is a constant, unshielded reality, reminding us that protection is a precious, rare gift. Mars is a frozen desert of faded potential. Our celestial neighbor, Mars, beckons with its rusty hue and whispered tales of a watery past. Yet beneath that alluring facade lies a world profoundly inhospitable to life, as we know it. It is a planet locked in a state of arrested development, a frozen desert where the very elements that foster and sustain life are absent or present in forms that actively repel it. The thin atmosphere, less than 1% the density of Earth's, offers little protection from the sun's harsh ultraviolet radiation and cosmic rays, making surface survival an impossible feat for most terrestrial organisms. This tenuous atmospheric blanket also means that liquid water, a cornerstone of life on Earth, cannot persist on the Martian surface. It would either freeze into ice or sublimate directly into vapor, leaving behind a parched and desolate landscape. While evidence strongly suggests that Mars once possessed a thicker atmosphere, perhaps even oceans and rivers, a catastrophic loss of its magnetic field billions of years ago allowed this precious atmosphere to be stripped away by the solar wind. Without this protective shield, the planet's interior cooled, its geological activity waned, and any potential for a self-sustaining biosphere effectively faded. The extreme temperature fluctuations, plummeting to as low as -153 degrees Celsius, -243 degrees Fahrenheit, at the poles during winter, further underscore the planet's frozen nature. Even at the equator during the Martian summer, temperatures rarely rise above a chilly 20 degrees Celsius, 68 degrees Fahrenheit, and often dip significantly below freezing at night. The soil itself is a stark reminder of this harsh reality, laced with perchlorates, compounds that are toxic to many forms of life and can interfere with biological processes. These perchlorates, while potentially offering a source of oxygen for future human explorers, also contribute to the planet's inhospitable character. The ancient riverbeds and dried-up lakebeds we observe are not testaments to a vibrant, living world, but rather haunting reminders of what once was, a ghost of a possibility that never fully bloomed. The potential for life on Mars, if it ever existed, seems to have been extinguished by a series of cosmic misfortunes, leaving behind a beautiful, yet barren monument to faded potential. The very conditions that allow Earth to thrive, a thick, protective atmosphere, a global magnetic field, abundant liquid water, and moderate temperatures, are conspicuously absent on Mars, transforming it from a potential cradle of life into a frigid, desolate expanse, a stark reminder of the delicate cosmic balance required for life to take root and flourish. The relentless radiation, the bone-chilling cold, and the suffocating thinness of the air conspire to create a world that, while endlessly fascinating to study, remains resolutely devoid of the vibrant biological tapestry we call home. The echoes of a wetter, perhaps even warmer, past are etched into its canyons and plains, but the present reality is one of frozen stillness, a world where the whispers of ancient water are carried on winds that offer no solace, no sustenance, and no embrace for the delicate spark of life. This enduring frozen state, this arrested evolution, paints Mars not as a failed Earth, but as a world that simply never received the sustained cosmic blessings necessary for life to truly flourish. And so, Mars stands as a silent sentinel, a testament to the profound fragility of planetary habitability, a frozen desert whispering of what might have been, reminding us that even a near twin can be a world of faded potential. Jupiter's gravity is an unstoppable crushing force. Imagine a world so immense, so massive, that its gravitational pull dictates the very dance of its celestial companions. This is Jupiter, the undisputed king of our solar system, a gas giant whose sheer bulk is a testament to the raw power of cosmic forces. Its diameter is over 11 times that of Earth, and its mass is more than 2.5 times that of all the other planets in our solar system combined. This colossal size translates into a gravitational field that is, as we've noted, an unstoppable crushing force. For any object venturing too close, whether it be a comet, an asteroid, or even a spacecraft, the pull of Jupiter is an inescapable embrace. This immense gravity is what has shaped the orbits of many smaller bodies in our solar system, acting as a cosmic shepherd, guiding and sometimes capturing them. It's a force that has been instrumental in the formation and evolution of our planetary neighborhood, clearing out debris fields and influencing the paths of celestial wanderers for billions of years. The pressure within Jupiter itself is, of course, unimaginable. At its core, the immense weight of the overlying atmosphere compresses hydrogen into a state known as metallic hydrogen, a bizarre substance that behaves like a liquid metal. This internal pressure, generated by its own colossal gravity, is a fundamental characteristic of the planet and a key factor in its unique geophysical processes. Even the atmosphere of Jupiter, a swirling maelstrom of clouds and storms, is a direct consequence of this powerful gravitational influence. The Great Red Spot, a storm larger than Earth, has raged for centuries, a testament to the dynamic and energetic nature of this giant world, all powered by the relentless force of its gravity. The moons of Jupiter, a retinue of over 80 known satellites, are also held captive by this overwhelming gravitational might. Their orbits are dictated by Jupiter, and in some cases, their very geology is sculpted by the tidal forces exerted by their massive parent planet. For instance, Io, the innermost of the Galilean moons, is volcanically active due to the intense gravitational tug-of-war between Jupiter and its other large moons, creating immense tidal heating that melts its interior. Europa, another of Jupiter's moons, is believed to harbor a vast ocean of liquid water beneath its icy crust, a possibility also linked to the tidal forces and internal heating generated by Jupiter's gravity. Ganymede, the largest moon in the solar system, is even larger than the planet Mercury, and it too orbits Jupiter, a testament to the planet's overwhelming gravitational dominion. This colossal gravitational influence is not just a passive force. It is an active sculptor of the solar system, a constant presence that has shaped the destiny of countless celestial bodies. It is a reminder that in the grand cosmic ballet, mass and gravity are the principal choreographers, their power absolute and their influence far-reaching. The sheer scale of Jupiter's gravity is a concept that is difficult for us to fully grasp, accustomed as we are to the gentler embrace of Earth's own gravitational field. But it is this very force that makes Jupiter such a unique and awe-inspiring entity, a giant whose presence fundamentally shapes the cosmic landscape around it. It is a force that, if we were to approach it directly, would utterly overwhelm us, crushing us into oblivion with its immense power. But from a safe distance, it is a magnificent spectacle, a reminder of the incredible forces that govern the universe. The relentless pull of Jupiter is a constant, unwavering force, a testament to its immense mass and the fundamental laws of physics that govern the cosmos. It is a force that has shaped our solar system and continues to play a vital role in its ongoing evolution. In the silent vastness, a giant breathes, its gravity a song of inescapable persuasion, shaping worlds with a gentle, yet absolute command. Saturn's rings are beautifully deceptive. When we gaze upon Saturn, our minds are immediately captivated by its iconic rings, a spectacle of unparalleled celestial artistry. They appear as solid, ethereal bands, a smooth, continuous disk of light and shadow encircling the majestic giant. This visual impression, however, is a profound deception, a testament to the vastness and complexity of the cosmos that often belies its true nature. These rings are not solid at all. Instead, they are a dynamic, ever-shifting collection of countless individual particles, ranging in size from microscopic dust grains to chunks of ice and rock as large as a small house. Each of these particles orbits Saturn independently, following its own trajectory, yet collectively, their sheer number and the delicate balance of gravitational forces create the illusion of a cohesive, unbroken structure. The particles themselves are primarily composed of water ice, which accounts for their dazzling reflectivity and brilliant white appearance. This ice, however, is not pristine. It is often mixed with darker, rocky material, and the particles are frequently coated in a fine dust, giving the rings their subtle variations in color and brightness. The origin of these rings is still a subject of scientific debate, but the prevailing theories suggest they formed relatively recently in Saturn's history, perhaps from the destruction of a moon or a comet that ventured too close to the planet and was torn apart by its immense gravitational pull. Alternatively, they may be remnants from the original formation of the solar system, material that never coalesced into a moon. The rings are incredibly thin for their vast width. While they can stretch hundreds of thousands of kilometers across, they are typically only a few tens of meters thick, a staggering ratio that further contributes to their illusion of solidity. This thinness means that if you were to somehow travel through them, you would find yourself in a vast expanse of empty space, punctuated by these individual, orbiting ice chunks. Within the rings, there are intricate structures and gaps, most notably the Cassini division, a prominent gap that separates the ring from the B ring. These divisions are not empty voids, but are maintained by the gravitational influence of Saturn's moons, particularly the small moon Mimas, whose orbital resonance with the particles in the Cassini division effectively clears them out. Other smaller moons, known as shepherd moons, orbit within or near the edges of the main rings, their gravity sculpting the edges and creating delicate wave patterns and kinks. The dance of these particles, influenced by Saturn's gravity, the tidal forces from its moons, and even the faint pressure of sunlight, is a constant, chaotic ballet. They collide, they grind against each other, and they are continually replenished by impacts from micrometeoroids. The deceptive beauty of Saturn's rings lies in this juxtaposition of immense scale and microscopic components, of apparent solidity and underlying emptiness, of a seemingly static masterpiece and a perpetually evolving dynamic system. They are a cosmic illusion, a grand performance of physics playing out on a planetary stage, reminding us that what we perceive as simple and singular is often a complex tapestry of countless individual elements. The rings are not a solid disk, but a vast, shimmering swarm of icy debris, each particle a tiny world in its own right, all participating in an ancient, ongoing cosmic waltz. In the grand theater of the cosmos, even the most solid-seeming beauty is but a fleeting arrangement of countless, independent whispers. Uranus spins on an improbable axis. Imagine, if you will, a colossal cosmic dancer, not gracefully pirouetting as we might expect, but rather rolling along its orbital path like a runaway barrel. This is the extraordinary orientation of Uranus, the seventh planet from our Sun. While most planets in our solar system exhibit a relatively upright spin, with their rotational axes tilted only slightly relative to their orbital planes, Uranus presents a stark and fascinating contrast. Its axis of rotation is tilted at an astonishing angle of approximately 97.8 degrees. This means that Uranus essentially orbits the Sun on its side, presenting a truly unique and, frankly, peculiar spectacle in the grand theater of our solar system. To comprehend the sheer oddity of this, consider Earth. Our planet's axis is tilted at a mere 23.5 degrees, a tilt that is responsible for the beautiful and predictable cycle of seasons we experience. This moderate tilt allows for distinct periods of warmth and cold, of growth and dormancy, shaping life as we know it. Now, amplify that tilt by more than 4 times, and you begin to approach the extreme orientation of Uranus. For a significant portion of its orbit, one of Uranus's poles points almost directly towards the Sun, experiencing continuous daylight for decades, while the other pole is plunged into perpetual darkness. Then, as the planet continues its journey around the Sun, the situation reverses, and the roles of light and shadow are swapped. The consequences of this extreme tilt are profound, and unlike anything seen on other planets within our solar system. For instance, the concept of seasons on Uranus is radically different. Instead of gradual shifts in temperature and daylight hours that we associate with spring, summer, autumn, and winter, Uranus experiences periods of intense, continuous sunlight or darkness that last for approximately 21 Earth years each. This leads to incredibly long and extreme seasonal variations. During the Uranian summer at one pole, that hemisphere receives constant sunlight, while the opposite hemisphere is in a deep, 21-year-long winter. This extreme solar illumination and prolonged darkness profoundly impacts the planet's atmosphere and weather patterns, creating unique meteorological phenomena that scientists are still working to fully understand. The prevailing scientific theory for this peculiar axial tilt attributes it to a catastrophic event in the early history of the solar system, likely a massive collision. It is hypothesized that a protoplanet, perhaps as large as Earth, slammed into Uranus billions of years ago. This cataclysmic impact would have been powerful enough to not only knock the planet onto its side, but also to dramatically alter its rotation, and possibly even eject a significant portion of its early atmosphere and crust, contributing to the formation of its unique ring system and the peculiar composition of its moons. This violent origin story is a stark reminder of the dynamic and often brutal processes that shaped our solar system. Furthermore, Uranus's magnetic field is also unusually oriented. Unlike most planets where the magnetic field is roughly aligned with the rotational axis, Uranus's magnetic field is tilted by about 60 degrees relative to its spin axis, and is also offset from the planet's center. This bizarre magnetic alignment is another consequence, scientists believe, of the massive impact that tilted the planet. The magnetic field plays a crucial role in protecting a planet from harmful solar radiation, and its unusual orientation on Uranus suggests a complex and perhaps less consistent shield against the solar wind. The very nature of day and night on Uranus is also a curious affair. Because of its extreme tilt, the sun does not rise and set in a predictable manner as it does on Earth. For extended periods, the sun might appear to circle the sky near one of the poles, or it might remain below the horizon for decades. This creates a truly alien experience of celestial movement, far removed from our familiar diurnal rhythm. The discovery of Uranus in 1781 by William Herschel marked a significant expansion of our known solar system. Initially, it was observed as a faint star, but its movement revealed it to be a planet. Its unusual tilt was not immediately apparent and took further observation to discern. The subsequent exploration and study of Uranus, particularly by the Voyager 2 spacecraft in 1986, provided us with our most detailed insights into this enigmatic world, revealing its faint rings, its numerous moons, and the peculiarities of its atmosphere and magnetic field, all shaped by its extreme inclination. The implications of Uranus's tilted axis extend to our understanding of planetary formation and evolution. It demonstrates that the processes that form planets are not uniform and can result in vastly different outcomes, even within the same solar system. The existence of such a dramatically tilted planet challenges our assumptions about what constitutes a typical planetary configuration and forces us to consider a wider range of possibilities when searching for worlds beyond our own. The study of Uranus, with its sideways spin, serves as a powerful reminder that the universe is not always bound by our expectations or our terrestrial experiences. It showcases the vastness of cosmic variation and the incredible diversity of worlds that can arise from the fundamental laws of physics. This off-kilter planet, in its silent, distant orbit, offers a profound lesson in the unpredictable beauty and surprising resilience of celestial bodies. And so, this rolling planet, Uranus, spins on its side, a testament to cosmic violence and the astonishing variety of worlds that populate our solar system, reminding us that even the most fundamental aspects of a planet, like its orientation, can be dramatically and beautifully unique. Neptune hides a core of crushing ice. Imagine, for a moment, a world so distant, so shrouded in the deep blue twilight of our solar system, that its very heart remains a profound mystery. Neptune, the eighth planet from our Sun, is a giant. A gas giant, yes, but beneath its swirling, tempestuous atmosphere of methane and hydrogen lies a realm of unimaginable pressure and extreme temperature. We often think of ice as something solid, something that melts under warmth, but on Neptune, ice takes on forms we can barely comprehend. This is not the delicate frost on a winter windowpane, nor the solid block in our freezer. This is supersonic ice, a state of matter where the atoms of oxygen and hydrogen, the very building blocks of water, are so compressed, so energized by the immense gravitational forces that they break free from their rigid crystalline structures. In this state, the oxygen atoms form a lattice, a sort of cage, through which the hydrogen nuclei, the protons, can flow like a liquid or even a gas. It's a bizarre, almost paradoxical state, where the fundamental components of water exist in a state that is neither fully solid nor fully liquid, but something entirely alien. This ice is incredibly dense, far denser than any ice we know on Earth, and it exists at temperatures that would vaporize anything familiar to us. The core of Neptune is thought to be a rocky, icy mixture, but the immense pressure, estimated to be in the millions of atmospheres, millions of times the pressure at sea level on Earth, forces these materials into these exotic, high-pressure phases. It's a pressure that could crush a starship, obliterate any known material, and transform familiar substances into entirely new forms. This dense, exotic ice likely makes up a significant portion of Neptune's mass, a hidden ocean of compressed water, ammonia, and methane, swirling around a potentially small rocky core. The sheer scale of this internal ocean, its alien composition, and the extreme conditions under which it exists speak to the vastness of the universe's capacity for surprise. It's a reminder that even the fundamental elements we know can behave in ways that defy our everyday intuition, especially when subjected to the grand forces of planetary formation and cosmic evolution. The deep interior of Neptune is a testament to the fact that what we perceive as ice is merely one manifestation of H2O, and that under the right circumstances, it can become a substance of crushing density and perplexing fluidity, a hidden sea of exotic matter at the edge of our solar system. And in the crushing, alien depths of Neptune, even the most familiar of molecules transforms into a state of profound, unseen wonder. Pluto's orbit is a dance of extreme distances. Our exploration of the celestial bodies that cannot sustain life as we know it leads us to a world that, for a time, held a place in our solar system's family portrait. Pluto. Once considered the ninth planet, Pluto was reclassified as a dwarf planet in 2006, a decision that sparked much debate, but one that underscores the sheer diversity of objects populating our cosmic neighborhood. Pluto's orbit is not like that of the familiar, nearly circular paths of the gas giants or even our own Earth. Instead, it is a journey of extreme distances, a solitary ballet performed across vast expanses of the Kuiper Belt. This region, a donut-shaped expanse beyond Neptune, is home to countless icy bodies, remnants from the solar system's formation. Pluto is the most prominent of these, but its orbital path is anything but stable or predictable in the way we might intuitively imagine. Pluto's orbit is highly elliptical, meaning it's more of an oval than a perfect circle. At its closest point to the Sun, called perihelion, Pluto is about 4.4 billion kilometers, 2.7 billion miles away. At its farthest point, aphelion, this distance stretches to a staggering 7.4 billion kilometers, 4.6 billion miles. This means that for a significant portion of its 248-year journey around the Sun, Pluto is closer to the Sun than Neptune, the eighth planet. This is a unique situation in our solar system. All other planets orbit the Sun in a predictable sequence, with each subsequent planet being farther out. Pluto's orbit is tilted at an angle of about 17 degrees relative to the plane of the 8 planets, and it is also eccentric, meaning it deviates significantly from a perfect circle. This eccentricity means that the gravitational influence of Neptune, the large gas giant whose orbit it crosses, is a significant factor in Pluto's celestial dance. The extreme distances involved in Pluto's orbit have profound implications for its environment. When Pluto is at its farthest point from the Sun, it receives only a tiny fraction of the sunlight that Earth does. Its surface temperature hovers around -230 degrees Celsius, -380 degrees Fahrenheit, cold enough to freeze gases like nitrogen and methane, which form a thin atmosphere when Pluto is closer to the Sun. This dramatic shift in distance means that Pluto's atmosphere can literally freeze and fall to the surface as snow or ice as it recedes from the Sun. This dynamic process, driven by the vast swings in solar radiation, is a testament to the extreme conditions faced by objects in the outer solar system. The sheer scale of these distances also means that Pluto is incredibly remote, a distant, frozen world on the fringes of our Sun's influence. Traveling to Pluto is an undertaking that requires immense time and energy, a journey that emphasizes the vastness of even our own solar system. The Kuiper Belt, where Pluto resides, is a realm of perpetual twilight, a cold and distant frontier where the sun is but a brilliant star, offering little warmth. The gravitational interactions within this region are complex, with the massive presence of Neptune playing a crucial role in shaping the orbits of objects like Pluto. This orbital eccentricity and inclination mean that Pluto's path is not a simple, predictable loop. It is a complex, weaving trajectory, influenced by the gravities of Neptune and other large objects in the Kuiper Belt. This dynamic interplay of forces prevents Pluto from ever colliding with Neptune, despite its orbit crossing Neptune's path. The two bodies are in what is known as a 2-3 orbital resonance, meaning that for every 3 orbits Neptune completes around the Sun, Pluto completes 2. This ensures a safe distance is maintained, a cosmic choreography that has played out for billions of years. The extreme distances also mean that Pluto experiences a very slow transition between its closest and farthest points from the Sun, a prolonged period of subtle environmental change. This slow, deliberate passage through the outer reaches of the solar system is a stark contrast to the more rapid cycles experienced by the inner planets. It is a journey measured in centuries, a testament to the immense scale of the solar system and the unique, solitary nature of Pluto's existence. The vast emptiness between celestial bodies is a constant reminder of the immense space that separates even our closest cosmic neighbors, and Pluto's orbit is a particularly striking example of this profound scale. Pluto's orbit is a lonely waltz across the solar system's farthest reaches, a reminder that distance itself can sculpt a world into something profoundly alien. The Sun's embrace is both life-giving and deadly. Our Sun, this magnificent star at the heart of our solar system, is the very engine of existence for Earth. Its gentle warmth, its radiant light, are the fundamental forces that allow life to flourish. Without the Sun, our planet would be a frozen, dark, and barren sphere, utterly devoid of the intricate dance of biology we know and cherish. It is the Sun's energy that powers photosynthesis, the miraculous process by which plants, the base of most food chains, convert light into sustenance. This energy warms our oceans, drives our weather patterns, and imbues our days with the light that guides our senses and our moods. The very rhythm of our lives, from the waking hours to the quiet of the night, is dictated by our star's benevolent cycle. It is a constant, dependable presence, a source of comfort and stability that, for millennia, humanity has looked to with reverence and gratitude. The sheer power contained within that distant, glowing orb is almost incomprehensible, yet it manifests as a gentle, life-sustaining embrace that reaches across the vastness of space to nurture our world. The delicate balance of solar radiation, filtered and moderated by our atmosphere, provides the perfect energetic environment for the complex chemistry of life to unfold. It is this constant, life-affirming influx of energy that allows for the intricate biochemical reactions that define living organisms, from the smallest microbe to the largest whale. The Sun's light not only fuels our planet's ecosystems, but also plays a crucial role in regulating our internal biological clocks, our circadian rhythms, helping us to feel awake and alive during the day and to prepare for rest as twilight descends. It is a fundamental component of our very being, woven into the fabric of our existence. However, this same celestial body, this font of life, also possesses a fierce and destructive potential. The Sun's embrace can, in moments, turn from a gentle warmth to a searing, annihilating force. Its surface is a turbulent inferno, constantly erupting with solar flares and coronal mass ejections, titanic bursts of energy and charged particles that can travel at incredible speeds. If these powerful events were to strike Earth directly, unimpeded, they would be catastrophic. The intense radiation could strip away our atmosphere, boil our oceans, and render the surface utterly uninhabitable. Our planet is protected by a remarkable shield, our magnetosphere, a protective bubble generated by the Earth's core, which deflects the majority of these harmful solar particles. Our atmosphere also plays a vital role, absorbing much of the sun's ultraviolet radiation, which, in high doses, is damaging to living cells. Yet even with these defenses, the sun's raw power is a constant reminder of our vulnerability. Solar storms, while often unseen, can disrupt our technologies, our satellites, our communication networks, and even our power grids. The very energy that sustains us, if unleashed without restraint, could obliterate us. It is a profound paradox. The source of our life is also a potential harbinger of our demise. This duality underscores the exquisite, and perhaps precarious, balance that allows life to exist on Earth. We are beneficiaries of a cosmic benevolence, but we also live under the constant, albeit usually distant, threat of our star's immense, untamed power. The sun's embrace is therefore a constant, subtle negotiation between life and destruction, a delicate dance that has allowed our planet to thrive. And so, the star that gives us life also reminds us of its fragility, a celestial paradox whispering of both our origins and our potential end. Moons can possess atmospheres, but not always habitable ones. Our journey through the solar system, a gentle drift from the sun outward, has revealed worlds of stark contrasts and surprising similarities. We've seen the fiery embrace of Venus, the frozen desolation of Mars, and the immense gravitational might of the gas giants. Now, our gaze turns to a less visited, yet profoundly fascinating category of celestial bodies: moons. For a long time, moons were often thought of as mere companions to their parent planets, passive satellites in a grand cosmic ballet. But as our understanding has deepened, we've discovered that some moons are worlds in their own right, capable of possessing atmospheres, those delicate veils of gas that can, under the right circumstances, hint at conditions conducive to life. Consider Titan, the largest moon of Saturn. It is a truly extraordinary place, unique not just among moons but in the entire solar system. Titan boasts a thick, nitrogen-rich atmosphere, denser than Earth's, with a significant amount of methane. This atmosphere creates a hazy, orange sky, obscuring the surface from direct view and leading to weather patterns, including methane rain and liquid methane lakes and rivers. It's a world with a hydrological cycle, albeit one based on hydrocarbons rather than water. The pressure at Titan's surface is about 1.5 times that of Earth at sea level, and its temperature is a frigid minus 179 degrees Celsius, minus 290 degrees Fahrenheit. While this extreme cold and the lack of liquid water as we know it make Titan uninhabitable by Earth-like life, the presence of a substantial atmosphere, complex organic chemistry, and liquid on its surface makes it a prime target in the search for understanding the potential for life beyond Earth, or at least for understanding the processes that might lead to it. Then there's Europa, a moon of Jupiter, which is thought to harbor a vast ocean of liquid water beneath its icy crust. While Europa itself has a very tenuous atmosphere, primarily composed of oxygen, it's the asterisk potential for a subsurface ocean, warmed by tidal forces from Jupiter, that makes it so intriguing. This subsurface ocean, shielded from the harsh radiation of space by the ice shell, could theoretically contain the necessary ingredients for life: water, energy sources, and organic molecules. However, the atmosphere we experience on Earth, the one that moderates our temperatures, provides breathable air, and shields us from harmful radiation, is absent on Europa's surface. The thin exosphere offers little protection and doesn't create the stable, temperate environment we associate with habitability. Even Venus, a planet we've already discussed as inhospitable, has a superdense atmosphere that creates immense surface pressure and scorching temperatures. But its atmosphere, while dominant, is not conducive to life as we understand it. Its composition, the extreme heat and the crushing pressure create a hellscape. This highlights a crucial point. Simply having an atmosphere is not enough. The composition, the density asterisk, the asterisk temperature, and the asterisk pressure of that atmosphere are all critical factors. The presence of an atmosphere on a moon, or any celestial body, is often a testament to a complex geological or chemical history. For instance, volcanic activity can release gases, contributing to an atmosphere. Tidal forces, like those exerted by Jupiter on its moons, can generate internal heat, potentially driving geological processes that release gases or maintain subsurface liquid water, which might then interact with a thin atmosphere. The solar wind, the stream of charged particles emitted by the sun, can also play a role. It can strip away atmospheres, but in some cases, interactions with atmospheric gases can create phenomena like auroras. The key takeaway is that an atmosphere is a vital component for habitability, but it's part of a much larger, intricate puzzle. We need an atmosphere that provides a stable temperature range, protects from harmful radiation, and possesses the right chemical composition. On moons like Titan, we see the fascinating spectacle of an atmosphere creating a dynamic, albeit alien, environment. On Europa, the potential for life lies hidden beneath the ice, with only a whisper of an atmosphere above. These distant worlds, with their gaseous veils, remind us that the conditions for life are incredibly specific, and that Earth's atmosphere, so familiar and taken for granted, is a truly remarkable and perhaps rare achievement in the grand tapestry of the cosmos. And so, we find that even a moon can wear a sky, yet that sky may be a chilling shroud rather than a gentle embrace. Exoplanets exist in astonishing variety. Beyond our familiar solar system, a universe of worlds unfolds, each a testament to the boundless creativity of cosmic processes. These exoplanets, worlds orbiting stars other than our Sun, are not merely distant replicas of Earth or the familiar gas giants. Instead, they present a staggering spectrum of sizes, compositions, temperatures, and orbital characteristics, challenging our preconceptions and expanding our understanding of what a planet can be. Imagine worlds vastly larger than Jupiter, so immense that they are classified as brown dwarfs, or tiny rocky spheres barely larger than our moon. Consider planets that orbit their stars in mere hours, completing a full revolution before Earth completes a single sunrise. Then there are those in distant, elongated orbits, spending eons in the frigid darkness before a brief, searing passage near their star. The sheer diversity extends to their fundamental nature. We have discovered hot Jupiters, gas giants inexplicably close to their parent stars, their atmospheres likely stripped away by intense radiation. There are super-Earths, rocky planets significantly more massive than our own, potentially harboring thicker atmospheres and even oceans under immense pressure. We find mini-Neptunes, worlds that defy easy categorization, possessing characteristics of both rocky planets and gas giants. Some exoplanets are tidally locked, meaning one side perpetually faces their star, creating extreme temperature gradients between eternal day and eternal night. Others might be rogue planets, wandering through interstellar space, unattached to any star, their origins a profound mystery. The chemical compositions of their atmospheres, when detectable, reveal an incredible range of possibilities, from the presence of exotic molecules to the potential for water vapor, methane, or even oxygen. Each discovery adds another brushstroke to the grand canvas of planetary formation, suggesting that the processes that sculpted our own solar system are but one of countless variations played out across the galaxy. The sheer number of exoplanets already confirmed, numbering in the thousands, is merely a glimpse into the true cosmic census, with estimates suggesting billions of planets in our galaxy alone. This immense variety underscores that our understanding of planetary science is still in its nascent stages, a continuous unfolding of the extraordinary. The universe, it seems, is a master of innovation, constantly presenting us with novel forms and configurations of celestial bodies that push the boundaries of our imagination and scientific inquiry. This astonishing diversity is not just a scientific curiosity. It is a profound reminder of the vastness and complexity of the cosmos, hinting at possibilities we are only just beginning to comprehend. The sheer act of existence for these distant worlds in their myriad forms speaks to the fundamental forces that shape the universe. In this grand cosmic theater, each unique exoplanet is a quiet whisper of possibility, reminding us that wonder is woven into the very fabric of existence. Habitable zones are not always truly habitable. The concept of a habitable zone around a star, often referred to as the Goldilocks zone, is a crucial starting point in our search for life beyond Earth. It's defined as the region where a planet's surface temperature could potentially allow liquid water to exist. This is a fundamental requirement, as we understand it, for life as we know it. However, this seemingly straightforward definition belies a far more complex reality. A planet residing within a star's habitable zone is by no means guaranteed to host life, or even to be hospitable to it. There are a multitude of factors that can render a planet within this seemingly ideal orbital band utterly uninhabitable. One of the most significant factors is the star itself. Not all stars are created equal, and their behavior can drastically alter the conditions on orbiting planets. For instance, younger, more active stars, particularly red dwarfs, are prone to frequent and intense stellar flares. These flares can strip away a planet's atmosphere, bombard its surface with harmful radiation, and even sterilize it. Even a planet comfortably within the habitable zone might experience such devastating outbursts that life simply cannot gain a foothold or survive long-term. The intensity and frequency of these flares are critical. A planet might be in the right orbital path, but the star's temper tantrums could make it a desolate, irradiated wasteland. Atmospheric composition is another paramount consideration. A planet might possess the ideal temperature for liquid water, but without a suitable atmosphere, that water would either freeze or evaporate into space. An atmosphere plays a vital role in regulating temperature through the greenhouse effect, shielding the surface from harmful ultraviolet radiation and providing the necessary gases for biological processes. A planet could have a thick, Venus-like atmosphere that traps too much heat, turning it into an inferno, or a thin, Mars-like atmosphere that offers little protection and allows water to sublimate directly into gas. The precise balance of gases, nitrogen, oxygen, carbon dioxide, and others, is critical, and even subtle differences can make a world inhospitable. Furthermore, the presence and dynamics of water itself are complex. While the habitable zone suggests the asterisk potential for liquid water, it doesn't guarantee its existence or its accessibility. A planet might have vast subsurface oceans, like some of Jupiter's and Saturn's moons, but life might be confined to these deep, dark realms, inaccessible to surface-dwelling organisms and difficult for us to detect. Alternatively, a planet could have had water in the past, but geological or atmospheric changes might have led to its complete loss. Tidal locking is another phenomenon that can affect habitability within the habitable zone. Planets orbiting close to their stars, particularly red dwarfs, can become tidally locked, meaning one side perpetually faces the star, becoming scorched, while the other side is frozen in eternal darkness. This creates extreme temperature gradients that are incredibly challenging for life to adapt to. Geological activity also plays a significant role. Plate tectonics, for example, is believed to be crucial for regulating a planet's climate over geological timescales. It helps recycle essential elements and minerals, and can contribute to the formation of oceans and continents. A planet lacking such geological dynamism might struggle to maintain stable conditions conducive to life. Conversely, excessive volcanism could release too many greenhouse gases, leading to runaway warming or spew out toxic gases. The internal heat of a planet also influences its magnetic field, which is essential for deflecting harmful stellar winds. Without a robust magnetic field, the atmosphere can be gradually eroded, leaving the surface exposed and vulnerable. The definition of the habitable zone is also a simplification. It typically considers a planet with Earth-like properties, such as a rocky composition and a significant amount of water. However, life could potentially exist in forms we haven't even imagined, on planets with very different compositions or in environments we currently deem hostile. But even within our current understanding, the habitable zone is merely a starting point, a first-pass filter. It identifies potential candidates, but a much deeper investigation into the planet's specific characteristics, its star, its atmosphere, its geology, its water content, and its orbital stability is required to determine true habitability. The habitable zone is a beautiful idea, a hopeful beacon, but the universe is replete with nuances that remind us that a theoretical possibility does not always translate into a lived reality. The theoretical embrace of a distant sun offers only a whisper of possibility, not a guarantee of a living world. The Goldilocks principle is more complex than it seems. The Goldilocks principle, often invoked when discussing the search for life beyond Earth, suggests that a planet must reside within a specific orbital distance from its star, not too hot, not too cold, but just right. This seemingly simple concept, named after the fairy tale, proposes that this habitable zone is where liquid water, a key ingredient for life as we know it, can exist on a planet's surface. However, as our understanding of planetary science and exoplanets expands, it becomes clear that this principle, while a useful starting point, is a significant oversimplification. The reality of habitability is far more nuanced, involving a complex interplay of factors that extend well beyond a planet's distance from its star. Consider the star itself. Not all stars are alike. Our Sun is a G-type main sequence star, relatively stable and long-lived. However, many stars are much cooler and dimmer red dwarfs, which are the most common type of star in the galaxy. Planets orbiting red dwarfs would need to be much closer to their star to receive sufficient warmth, placing them within the star's habitable zone. But this proximity comes with its own set of challenges. Red dwarfs are often prone to intense stellar flares, bursts of radiation that could strip away a planet's atmosphere and bombard its surface with harmful particles, making life exceedingly difficult, if not impossible. Furthermore, planets in close orbits around red dwarfs are often tidally locked, meaning one side perpetually faces the star, experiencing extreme heat, while the other is locked in eternal darkness and cold. This creates drastic temperature gradients that could prevent the stable conditions necessary for life. Then there is the planet's atmosphere. A planet's atmosphere plays a crucial role in regulating its temperature through the greenhouse effect. Venus, for instance, is closer to the sun than Earth, yet it is a scorching inferno. This is due to its incredibly dense atmosphere, composed primarily of carbon dioxide, which traps an enormous amount of heat, leading to runaway greenhouse conditions. Conversely, a planet with a very thin atmosphere might struggle to retain any heat, even if it were within the traditional habitable zone. The composition of the atmosphere is also critical. While greenhouse gases like carbon dioxide and water vapor can trap heat, certain gases can have devastating effects, as seen on Venus. The presence of an ozone layer, for example, is vital for protecting life from harmful ultraviolet radiation from the star, a feature not solely dependent on a planet's orbital position. The size and mass of a planet are also significant considerations. Larger, more massive planets are more likely to retain a substantial atmosphere and possess a molten core, which can drive geological activity like plate tectonics. Plate tectonics is thought to be crucial for long-term habitability, as it helps regulate carbon dioxide levels in the atmosphere, preventing the planet from becoming too hot or too cold over geological timescales. It also recycles nutrients and creates diverse geological environments that could foster the evolution of life. Smaller planets like Mars may have lost much of their atmosphere over time, rendering them inhospitable. The presence of a magnetic field is another vital, often overlooked factor. A global magnetic field acts as a shield, deflecting charged particles from the star and cosmic rays, which can otherwise erode a planet's atmosphere and damage organic molecules essential for life. Earth's robust magnetic field is a key reason why we can exist on its surface, without being constantly bombarded by harmful radiation. Without such a shield, even a planet within the ideal orbital distance might be rendered sterile. Furthermore, the concept of the habitable zone itself is not static. It changes over a star's lifetime as the star evolves and its luminosity increases or decreases. A planet that is habitable today might not be in the distant future, and vice versa. Also, internal heat sources, such as radioactive decay within a planet's core, can contribute to maintaining liquid water, even in subsurface oceans, as is suspected to be the case on some of Jupiter's and Saturn's moons like Europa and Enceladus. These moons are far outside the traditional habitable zone, yet the potential for life exists beneath their icy shells, powered by tidal forces and internal geological activity. The composition of a planet's crust and mantle, the availability of essential elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, and even the presence of a large moon to stabilize axial tilt, can all play a role in determining long-term habitability. The just right of the Goldilocks principle is not a single, fixed point, but rather a dynamic and multifaceted range of conditions that must be met. It is a beautiful idea, a guiding star in our cosmic quest, but it is merely the first step in a much grander, more intricate dance of planetary evolution and cosmic chance. The simple warmth of a star is but a single thread in the vast tapestry of life's possibility. Water is essential, but not sufficient for life. Water, that most ubiquitous and vital of substances, is indeed a cornerstone for the life we understand. It is the solvent of life, the medium through which countless biochemical reactions can occur, dissolving nutrients, transporting them within cells, and facilitating the intricate dance of metabolism. On Earth, wherever we find liquid water, we tend to find life, from the deepest oceanic trenches to the aridest deserts where it may be hidden beneath the surface. Its unique properties, its polarity, its high specific heat capacity that stabilizes temperatures, its ability to expand when it freezes, thus allowing aquatic life to survive beneath ice, all contribute to its indispensable role. Without liquid water, the complex organic molecules that form the basis of life as we know it would struggle to assemble, to interact, and to persist. Think of the vast oceans that cover our planet, teeming with diversity, or the microscopic organisms that thrive in a single drop of dew. Water is the cradle, the transport system, and the very essence of biological processes. However, and this is where the cosmic perspective gently reminds us of the intricate tapestry of existence, water alone, even in its liquid form, does not guarantee life. For life to truly take hold and flourish, a multitude of other factors must align. Consider Mars, a planet that scientists believe once harbored significant amounts of liquid water, perhaps even vast oceans. Yet today, it is a cold, dry, and seemingly barren world. The water that may remain is largely frozen, and the surface conditions are incredibly harsh. The thin atmosphere offers little protection from harmful radiation, the temperatures are frigid, and the atmospheric pressure is so low that liquid water would rapidly boil away or freeze. This stark reality tells us that while water is a necessary ingredient, it is not a sufficient one. There are other planets and moons in our solar system and beyond that are known to possess, or are suspected to possess, subsurface oceans of liquid water. Europa, one of Jupiter's moons, and Enceladus, a moon of Saturn, are prime examples. These icy worlds may harbor vast liquid water oceans beneath their frozen shells, warmed by tidal forces from their parent planets. While the presence of water is incredibly exciting for astrobiologists, the question of whether life has actually arisen there remains unanswered. We must consider the availability of essential chemical elements beyond just hydrogen and oxygen. The carbon, nitrogen, phosphorus, sulfur, and other elements that form the building blocks of organic molecules. We must consider a source of energy, whether it be sunlight, less likely in subsurface oceans, or chemical energy derived from geological processes. We must consider the stability of these environments over geological timescales, offering life the opportunity to emerge and evolve. The presence of water is a powerful indicator, a beacon of possibility, but it is only one crucial piece of a much larger, more complex cosmic puzzle. The silent presence of water on a world, though vital, whispers only a single note in the grand symphony of life's potential. Atmospheric pressure is a delicate balance. Imagine standing on the surface of a planet, a thin veil of gas surrounding you, holding you gently, yet firmly in place. This is the essence of atmospheric pressure, a force so pervasive we often forget its profound influence on the very possibility of life as we know it. On Earth, our atmosphere exerts a constant, measurable pressure, an invisible embrace that allows liquids to remain liquid, enables us to breathe, and protects us from the harsh vacuum of space. This pressure isn't static. It varies with altitude, temperature, and weather patterns, but within a remarkably narrow range, it creates the conditions necessary for biological processes to flourish. Consider the sheer weight of the air above us. At sea level, this weight presses down with approximately 14.7 pounds per square inch, or about 1 kilogram per square centimeter. This might sound like a lot, but our bodies are perfectly adapted to it, with internal pressures that equalize the external force. If we were to suddenly find ourselves in a vacuum like on the moon, this internal pressure would cause our bodily fluids to boil, a catastrophic and immediate consequence. Conversely, on a planet with a significantly denser atmosphere like Venus, the pressure can be over 90 times that of Earth's at sea level, enough to crush a submarine designed for our oceans. This crushing weight would not only be physically destructive, but would also dramatically alter the behavior of matter, making the existence of liquid water, and thus life as we understand it, virtually impossible. The composition of an atmosphere also plays a critical role in its pressure and its ability to support life. Earth's atmosphere, a carefully curated blend of nitrogen, oxygen, and trace gases, provides the right pressure for liquid water to exist across a wide range of temperatures. On Mars, the atmosphere is incredibly thin, less than 1% of Earth's pressure. This low pressure means that water, if it were to exist as a liquid on the surface, would rapidly boil away into vapor. Even if temperatures were suitable, the atmospheric pressure simply wouldn't permit it. For life to arise and persist, this delicate balance of pressure, temperature, and atmospheric composition must be maintained. It's a cosmic tightrope walk, where even slight deviations can lead to vastly different and often inhospitable planetary environments. The pressure we experience every day is not just a physical phenomenon. It's a vital component of Earth's life-sustaining architecture, a silent guardian that allows the intricate dance of biology to unfold. It is a testament to the precise and often subtle conditions that make our world a haven for life. The gentle pressure of our atmosphere is the quiet breath that cradles existence. Magnetic fields shield worlds from stellar winds. Imagine for a moment the silent, invisible dance of forces that governs our solar system. At its heart, our sun, a colossal furnace of nuclear fusion, doesn't just radiate light and warmth. It also spews out a constant stream of charged particles, electrons, protons, and heavier ions, a phenomenon we call the solar wind. This solar wind, while seemingly ethereal, carries immense energy and can be incredibly destructive. It's a relentless outward flow, a cosmic breath that unimpeded could strip away atmospheres, erode planetary surfaces, and render a world utterly uninhabitable. Yet here on Earth, we are remarkably protected. This protection is largely thanks to a powerful, invisible shield generated deep within our planet, our magnetic field. This field, a complex tapestry of lines extending far out into space, forms what we call the magnetosphere. It acts like a cosmic umbrella, deflecting the vast majority of these energetic particles from the sun. When the solar wind encounters the magnetosphere, it's guided around our planet, rather than slamming directly into our atmosphere. Think of it as a force field, a dynamic bubble that warps and bends to absorb the impact. Without this magnetic embrace, our atmosphere would likely have been stripped away eons ago, much like what scientists believe may have happened to Mars. This magnetic field isn't static. It ebbs and flows, influenced by the sun's activity and internal planetary dynamics. Auroras, those breathtaking displays of light in our polar skies, are a visible manifestation of this interaction. They occur when some of the charged particles from the solar wind are funneled along magnetic field lines into our upper atmosphere, exciting the gases and causing them to glow. It's a beautiful reminder of the constant, unseen battle being waged to preserve our world. The strength and stability of a planet's magnetic field are therefore critical factors in its potential for harboring life. Planets like Venus, which lacks a significant global magnetic field, have had their atmospheres eroded over time, contributing to their current infernal conditions. Mercury, being so close to the Sun and with a relatively weak magnetic field, is also exposed to much harsher bombardment. The presence of a robust magnetosphere is not just a passive shield. It's an active guardian, a fundamental requirement for the long-term stability of an atmosphere, and consequently, for the possibility of life as we know it. The very existence of our breathable air, the integrity of our landscapes, and the potential for complex life to evolve and persist owe a profound debt to this unseen, ever-present force. It's a testament to the intricate, interconnected systems that make our planet a haven in the vastness of space. And so, the silent strength of our planet's inner heart projects an invisible shield, a cosmic grace that cradles our world in the face of stellar storms, allowing life to unfurl in its gentle embrace. Plate tectonics recycles planets. Imagine the Earth, not as a static sphere, but as a dynamic, ever-changing entity, a cosmic sculptor constantly reshaping its own form. This grand process, known as plate tectonics, is far more than just the rumbling of earthquakes or the slow drift of continents. It's a fundamental mechanism that has, over eons, played a crucial role in making our planet habitable, and its absence on other worlds dramatically highlights why Earth stands apart. At its heart, plate tectonics involves the Earth's lithosphere, the rigid outer shell comprising the crust and the uppermost part of the mantle, being broken into numerous large and small pieces called tectonic plates. These plates aren't merely floating, they are in constant, albeit incredibly slow, motion, driven by the immense heat generated deep within our planet. This internal heat, a legacy of Earth's formation and the radioactive decay of elements, creates convection currents within the semi-fluid asthenosphere, the layer of the mantle just beneath the lithosphere. These currents act like a slow, viscous conveyor belt, dragging the overlying plates along. Where these plates meet, at what are called plate boundaries, the most dramatic geological activity occurs. There are three main types of boundaries: divergent, where plates move apart; convergent, where they collide; and transform, where they slide past each other. At divergent boundaries, molten rock or magma rises from the mantle to fill the gap, creating new crust. This is happening, for instance, along the Mid-Atlantic Ridge, a vast underwater mountain range. At convergent boundaries, the outcome depends on the type of crust involved. If oceanic crust collides with continental crust, the denser oceanic plate is forced beneath the continental plate in a process called subduction. This subducted material melts as it descends into the hotter mantle, fueling volcanic activity on the surface, forming arcs of volcanoes like the Andes. If two continental plates collide, neither can easily subduct, leading to immense crumpling and uplift, creating towering mountain ranges like the Himalayas. Transform boundaries, where plates grind past each other horizontally, are responsible for many earthquakes, as the immense stress built up is suddenly released. So, how does this recycling contribute to habitability? Firstly, plate tectonics is a critical component of the carbon cycle. Carbon dioxide, a greenhouse gas essential for regulating Earth's temperature, is released into the atmosphere through volcanic outgassing. Without plate tectonics, this volcanic activity would cease, and over millions of years, the CO2 would be locked away in rocks, leading to a runaway cooling of the planet, much like what is believed to have happened on Mars. Conversely, subduction at convergent boundaries pulls carbon-bearing rocks back into the mantle, effectively recycling carbon and preventing a runaway greenhouse effect, maintaining a stable, temperate climate over geological timescales. Secondly, plate tectonics helps to renew the Earth's surface. Erosion and weathering constantly wear down mountains and alter landscapes. Volcanic activity and mountain building, driven by plate tectonics, create fresh rock and new landforms, providing diverse habitats for life to colonize and evolve. Without this constant rejuvenation, the Earth's surface might become geologically stagnant and less dynamic, potentially limiting the evolution of complex life. Furthermore, the generation of new crust at divergent boundaries contributes to the formation of ocean basins, which are crucial for regulating climate and supporting marine ecosystems. The movement of continents also influences ocean currents and atmospheric circulation patterns, further shaping climate and habitability. On planets like Venus, which lacks significant plate tectonics, heat builds up beneath the surface, leading to catastrophic volcanic resurfacing events, rather than the gradual, controlled recycling seen on Earth. This lack of a regulating mechanism contributes to Venus's extreme surface temperatures and crushing atmospheric pressure. Mars, on the other hand, has a thick, stagnant crust. While it once may have had some tectonic activity, it appears to have largely ceased, leading to a loss of its atmosphere and water, and a dramatic cooling of the planet. The internal heat engine of Earth, driving plate tectonics, is what keeps our planet geologically alive, constantly renewing its surface, regulating its climate, and providing the dynamic environment that life needs to thrive and persist. It's a slow, majestic process, a planetary breath that sustains our world. And so, the very ground beneath our feet is a testament to a planet that breathes, a world perpetually renewed by its own internal fires. The right mix of elements is crucial. Life, as we understand it, is a symphony of specific chemical elements, a delicate arrangement that has taken billions of years to compose on Earth. It's not enough to simply have the building blocks. They must be present in the right proportions, interacting in just the right ways to spark and sustain the intricate dance of biology. Consider carbon, the backbone of organic molecules. It's incredibly versatile, capable of forming long chains and complex structures that are the foundation of proteins, carbohydrates, fats, and DNA. Without abundant, accessible carbon, the very scaffolding of life would be impossible. Then there's hydrogen and oxygen, fundamental to water, the universal solvent that allows chemical reactions to occur within living cells. Water isn't just a passive medium. Its unique properties, its polarity, its high heat capacity, its ability to expand when frozen are all vital for life's processes. Nitrogen, too, plays a critical role, forming a significant part of amino acids and nucleic acids, and cycling through the environment in ways that make it available to organisms. Phosphorus is essential for energy transfer within cells, forming the backbone of ATP, adenosine triphosphate, the energy currency of life. It's also a key component of DNA and RNA. Sulfur contributes to the structure and function of many proteins, forming disulfide bonds that stabilize their three-dimensional shapes. Even trace elements, present in minuscule amounts, are indispensable. Iron, for instance, is crucial for oxygen transport in many organisms, as seen in hemoglobin. Magnesium is vital for photosynthesis, forming the central atom in chlorophyll. Without these elements, and many others like potassium, sodium, and calcium, present in the correct ratios and readily available, the complex biochemical pathways that define life simply could not emerge or persist. The precise abundance and accessibility of these elements, dictated by geological processes and planetary evolution, are therefore not accidental but a fundamental prerequisite for a living world. The formation of planets like Earth, with its specific composition and dynamic geological activity, has ensured that this crucial elemental mix is present and continuously recycled, providing the raw materials for life to arise and thrive. The cosmic recipe for life requires not just the ingredients, but the exact measure and the right conditions for them to blend. In this vast cosmic pantry, Earth holds the perfect blend, a quiet testament to elemental harmony. Life may arise from unexpected chemical reactions. Consider the very beginnings of life, not as a sudden spark, but as a slow, intricate dance of molecules. On early Earth, long before complex organisms, the atmosphere was a very different place. It was likely rich in gases like methane, ammonia, water vapor, and carbon dioxide, with very little free oxygen. Into this primordial soup, energy rained down from lightning strikes, from ultraviolet radiation bathing the planet, and from volcanic activity. These energies acted as catalysts, breaking apart simple molecules and allowing their constituent atoms to recombine in novel ways. The famous Miller-Urey experiment in the 1950s provided a compelling glimpse into this process. By simulating the conditions of early Earth in a laboratory, Stanley Miller and Harold Urey passed electrical sparks through a mixture of gases. Within days, they observed the formation of amino acids, the fundamental building blocks of proteins, which are essential for all known life. This was a groundbreaking discovery, demonstrating that the complex organic molecules necessary for life could indeed arise spontaneously from inorganic matter under plausible early Earth conditions. But the story doesn't end with amino acids. Further research has shown that other essential biomolecules, such as nucleotides, the building blocks of RNA and DNA, sugars and lipids, components of cell membranes, can also be synthesized through similar abiotic chemical reactions. These reactions might have occurred in various environments: in shallow pools of water, in hydrothermal vents on the ocean floor where chemicals are abundant, or even on mineral surfaces that could have acted as catalysts, concentrating reactants and facilitating reactions. Think of it as a cosmic recipe. The ingredients were abundant in the early universe and on early Earth. The energy was the heat and light. The process was chemistry, a relentless, patient exploration of possibilities. Over vast stretches of time, these simple chemical reactions, driven by energy and chance, began to assemble increasingly complex structures. These structures, through a process of self-organization, may have started to exhibit rudimentary forms of replication or metabolism, the very hallmarks of life. The key insight here is that life might not have required a singular, specific event, but rather a series of cumulative chemical successes. It's about the inherent tendency of matter, under the right conditions, to organize itself into more complex forms. Imagine countless tiny chemical experiments happening simultaneously across the globe, each with a minuscule chance of success, but with the sheer scale of the planet and the vastness of geological time making those chances significant. This perspective shifts our understanding of abiogenesis, the origin of life from non-living matter. It suggests that life isn't necessarily a miraculous, improbable event, but rather a natural consequence of the laws of physics and chemistry operating in a suitable environment. It implies that the processes that led to life on Earth might not be unique to our planet. If the right conditions and ingredients are present elsewhere, similar chemical pathways could, in principle, lead to the emergence of life on other worlds. The journey from simple inorganic molecules to self-replicating entities is incredibly complex, and many questions remain unanswered. We don't fully understand the precise sequence of steps, the specific environmental niches, or the exact catalysts involved. However, the evidence strongly suggests that life's genesis was a chemical phenomenon, a testament to the universe's capacity for emergent complexity. It's a reminder that the extraordinary can arise from the seemingly ordinary, through patience, energy, and the fundamental dance of atoms. From the simplest of elements, a symphony of existence can begin to compose itself. The universe is vastly more hostile than welcoming. When we look up at the night sky, it's easy to be enchanted by the twinkling lights, the distant galaxies, and the sheer immensity of it all. It's a vista that inspires wonder, curiosity, and a deep sense of connection to something far grander than ourselves. Yet, beneath this captivating beauty lies a stark reality. The vast majority of the universe is not a place where life, as we understand it, could possibly take hold. It is, in many ways, profoundly hostile. Consider the sheer emptiness of space. It's a vacuum, devoid of air to breathe, with temperatures that can plummet to near absolute zero or soar to extreme highs depending on proximity to stars. Cosmic rays, energetic particles streaming from supernovae and other violent celestial events bombard everything, capable of damaging DNA and stripping away atmospheres. Then there are the stars themselves. While our Sun is a relatively stable, life-sustaining star, many stars are far more volatile. Red dwarfs, the most common type of star, are prone to powerful solar flares that could sterilize any nearby planets. Larger stars live fast and die young in spectacular supernova explosions, releasing immense amounts of radiation that can obliterate life across vast interstellar distances. Even within our own solar system, the dangers are evident. Mercury, with its scorching days and freezing nights, lacks any substantial atmosphere to regulate temperature or shield its surface. Venus, shrouded in a runaway greenhouse effect, has an atmosphere so dense and toxic, with surface temperatures hot enough to melt lead, that it's akin to being at the bottom of a boiling ocean. Mars, while once thought to be a more hospitable neighbor, is now known to be a frigid desert, its atmosphere too thin to retain heat or offer significant protection from radiation, and its surface bathed in harmful ultraviolet rays. Beyond the immediate neighborhood, the conditions become even more extreme. The crushing gravity of gas giants like Jupiter and Saturn would make solid surfaces impossible, while their intense magnetic fields and radiation belts would be lethal. The very composition of many celestial bodies is inhospitable. Many moons and planets are composed of exotic materials or exist in states of matter that are utterly alien to life as we know it, under pressures and temperatures that defy our everyday experience. Even on planets that might reside within a star's habitable zone, that theoretical region where liquid water could exist on the surface, there are myriad other challenges. The planet might be tidally locked, with one side perpetually scorched and the other frozen. It might lack a protective magnetic field, leaving its atmosphere vulnerable to being stripped away by stellar winds. The planet might be bombarded by frequent asteroid impacts, or its star might be too active. The processes that lead to the formation of planets and stars are often violent and chaotic. Supernovae, the explosive deaths of massive stars, enrich the cosmos with heavy elements necessary for life, but they also release devastating waves of radiation. The early universe was dominated by hydrogen and helium, with little in the way of the complex chemistry that underpins biology. It took billions of years of stellar evolution and galactic recycling for the raw materials of life to become sufficiently widespread. Even the discovery of exoplanets, while incredibly exciting, reveals a universe teeming with worlds that are far from Earth-like. We find planets orbiting too close or too far from their stars, planets made entirely of rock or gas, planets with extreme orbital eccentricities, and planets subjected to the gravitational tugs of multiple stars. The sheer number of variables required for life to emerge and persist is staggering. It requires a stable star, a planet with the right size and composition, a protective atmosphere, a magnetic field, the presence of liquid water, and a long period of relative cosmic calm. When we weigh the immense scale of the universe against the narrow set of conditions that appear to be necessary for life, it becomes clear that Earth is not a typical planet. It is, in fact, an extraordinary anomaly, a precious haven in a cosmos that is overwhelmingly indifferent and often actively hostile to the delicate spark of existence. In this vast, silent expanse, our small, vibrant world is a rare and precious exception, a testament to the delicate dance of chance and circumstance that allows life to bloom. Our solar system is a rare cosmic coincidence. The arrangement of our solar system, with its inner rocky planets and outer gas giants, is not a guaranteed outcome of planetary formation. While we once thought this configuration might be common, observations of exoplanetary systems reveal a far more chaotic and diverse reality. Many stars host systems with entirely different architectures. Some have multiple super-Earths or mini-Neptunes orbiting very close to their star, while others have giant planets in highly eccentric, or elliptical, orbits that would sweep through the inner solar system, disrupting any nascent terrestrial worlds. The relatively stable, ordered orbits of our planets, particularly the clear separation between the terrestrial and Jovian realms, and the presence of a protective asteroid belt that largely prevents planetesimals from the outer solar system from impacting the inner planets, are indeed remarkable. This stability has allowed Earth to evolve over billions of years without constant bombardment that could sterilize it or strip away its atmosphere. The specific mass and composition of Jupiter, for instance, plays a crucial role in deflecting many comets and asteroids that might otherwise pose a significant threat to Earth. Without this gravitational shield, our planet's history might have been very different, perhaps far less conducive to the development and sustained presence of life. Furthermore, the precise positioning of the gas giants, preventing a wholesale inward migration that could have destabilized the inner solar system, is a fortunate circumstance. The sheer number of variables involved in planetary system formation, the initial mass and composition of the protoplanetary disk, the gravitational interactions between forming planets, the influence of nearby stars, and the specific evolutionary path of the host star, makes the emergence of a solar system like ours, with its particular balance and stability, a statistically improbable event. It is a cosmic alignment of circumstances that, when viewed against the backdrop of the universe's vastness and the myriad ways planetary systems can form, appears exceptionally fortunate. The gentle dance of our planets, the protective presence of our larger neighbors, and the relative quiet of our cosmic neighborhood are not necessarily the norm, but rather a precious and perhaps uncommon outcome of the universe's creative processes. This ordered ballet, so conducive to life's slow unfolding, is a testament to the intricate and often serendipitous nature of cosmic evolution. And in this vast, chaotic expanse, our orderly celestial family spins, a fortunate whisper in the grand silence. The search for extraterrestrial life is a search for ourselves. When we gaze outward, scanning the cosmic ocean for any whisper of life beyond our own blue marble, we are, in a profound and often unconscious way, looking inward. The very questions we pose to the universe: are we alone? What forms might life take? How does life begin? Are reflections of our own deepest curiosities about our origins, our purpose, and our place in the grand tapestry of existence. The criteria we use to define habitability, the signatures we seek in distant atmospheres, are all derived from our understanding of life as it exists here, on Earth. We project our own biological and chemical frameworks onto the unknown, hoping to find echoes of ourselves in the vast silence. This isn't necessarily a limitation, but rather a natural consequence of our limited perspective. We can only truly understand what we can relate to, and our frame of reference is the only life we know. Therefore, every discovery, every non-discovery, in the search for extraterrestrial intelligence or even simple microbial life, teaches us something fundamental about ourselves. If we find life that is remarkably similar to ours, it might suggest a universal set of biological pathways, a common cosmic blueprint. If we find life that is utterly alien, defying all our expectations, it would expand our very definition of what life is asterisk, forcing us to reevaluate our own biological uniqueness, and perhaps even our assumptions about consciousness and intelligence. The search is not just about finding other beings. It's about refining our understanding of what it means to be alive, what it means to be conscious, and what makes this particular spark of existence so precious. It is a journey of self-discovery, mirrored in the starlight, a quest to understand the universal principles that might govern existence, and in doing so, to better understand the singular miracle that is life on Earth. This outward exploration is, in essence, the most profound form of introspection, a cosmic mirror reflecting our own deepest questions back at us, illuminated by the light of distant stars. It is a testament to our innate drive to connect, to understand, and to find meaning in the immensity of the cosmos. In seeking the alien, we illuminate the familiar, finding ourselves in the vastness we explore. The conditions for life evolved over billions of years. Our journey through the solar system, and indeed our contemplation of the vast cosmos, often leads us to a profound realization. The Earth, as we know it, is not a static, preordained cradle of life. Instead, it is the product of an unimaginably long and intricate process of evolution, a cosmic ballet of geological, chemical, and astronomical events that, over billions of years, sculpted a world capable of nurturing and sustaining the intricate tapestry of life we see today. This wasn't an overnight creation. It was a gradual unfolding, a slow, patient refinement of planetary conditions. Imagine the early Earth, a molten sphere bombarded by asteroids, its atmosphere a toxic brew of gases utterly inimical to life as we understand it. For eons, this was the reality. Volcanic activity was rampant, spewing forth gases that would eventually form our oceans and atmosphere. The very building blocks of life, the complex organic molecules, were likely synthesized in this primordial soup, perhaps in deep-sea hydrothermal vents or through lightning strikes in the early atmosphere. This was a time of immense energy, of raw materials being churned and transformed. As the Earth cooled, a crucial step occurred, the formation of liquid water. Water is, of course, the universal solvent, the medium in which the complex chemistry of life can occur. The presence of vast oceans, formed from the condensation of water vapor released by volcanoes, was a monumental shift. These oceans absorbed much of the initial heat and provided a stable environment for early chemical reactions to proceed. But even with water, the atmosphere was still a far cry from what we breathe today. It was rich in carbon dioxide, methane, and ammonia, and crucially, lacked significant amounts of free oxygen. Photosynthesis, the process that would revolutionize Earth's atmosphere, had not yet evolved. The emergence of the first life forms, simple single-celled organisms, was a turning point. These early microbes, existing in the anaerobic depths of the oceans, began to alter their environment in subtle but profound ways. Over hundreds of millions of years, some of these organisms developed the ability to harness sunlight for energy, a process known as photosynthesis. This was a slow revolution. Initially, the oxygen produced was quickly absorbed by the iron in the oceans, creating vast deposits of banded iron formations, a geological testament to this early atmospheric transformation. But eventually, the oceans became saturated, and free oxygen began to accumulate in the atmosphere. This accumulation of oxygen was a double-edged sword. For the anaerobic life forms that had thrived for so long, oxygen was a poison, leading to a mass extinction event known as the Great Oxygenation Event. But for a new wave of life, one that could utilize oxygen for more efficient energy production, it was an unprecedented opportunity. This led to the evolution of more complex, multicellular organisms. The development of the ozone layer, a shield against the sun's harmful ultraviolet radiation, was another critical evolutionary step, allowing life to eventually move from the oceans onto land. The Earth's geological processes also played a vital role. Plate tectonics, the slow movement of the Earth's crust, constantly reshapes the planet, recycling nutrients, creating new landmasses, and driving volcanic activity that releases essential gases. The Earth's magnetic field, generated by its molten core, protects the atmosphere from being stripped away by the solar wind, a constant stream of charged particles from the sun. Without this magnetic shield, our atmosphere would be far thinner, and life would be much more vulnerable to radiation. The evolution of life itself, in turn, has continued to shape the planet. Plants have altered the atmospheric composition, influencing climate. The development of complex ecosystems has created intricate feedback loops that maintain a delicate balance. Even the way life interacts with the soil and water has a profound impact on the planet's chemistry. It's a continuous, dynamic interplay between the planet and its inhabitants, a co-evolutionary dance that has spanned billions of years. This long, slow process of evolution highlights just how contingent life on Earth is. It wasn't a predetermined outcome, but a series of fortunate events and gradual adaptations. The conditions that allow us to exist here are not inherent or guaranteed. They are the result of an immense cosmic lottery, played out over eons, that has gifted us this unique and precious planetary home. And so, the conditions for life on this world were not a gift bestowed at creation, but a masterpiece painstakingly crafted by the slow, relentless hand of time. Even Earth-like, exoplanets may lack key ingredients. The quest for planets beyond our solar system, exoplanets, has revealed a breathtaking diversity of worlds. Among these discoveries, a significant portion are categorized as potentially Earth-like, residing within the habitable zone of their stars, that region where liquid water could theoretically exist on a planet's surface. This tantalizing prospect fuels our imagination, conjuring images of alien landscapes, perhaps teeming with life. However, as our understanding of planetary formation and the intricate requirements for life deepens, it becomes clear that simply being Earth-like in size and location is far from a guarantee of habitability. The term Earth-like itself is a simplification, a convenient descriptor that masks a complex web of necessary conditions, many of which are incredibly difficult to ascertain from light years away. One of the most fundamental missing ingredients, even on seemingly promising exoplanets, can be a substantial, stable atmosphere. While we can detect the presence of atmospheres, determining their precise composition, density, and long-term stability is a monumental challenge. An atmosphere is not just a blanket of gas, it's a dynamic shield. It regulates temperature, preventing extreme fluctuations between day and night. It provides the necessary pressure for liquid water to exist. It can also shield the surface from harmful radiation, both from the host star and from cosmic rays. A thin atmosphere, or one composed of inhospitable gases, would render a planet barren, regardless of its position in the habitable zone. Consider the atmospheric pressure on Earth. It's a finely tuned balance that allows for the complex chemistry of life as we know it. Even a slight deviation could have catastrophic consequences. Furthermore, the presence of a global magnetic field like Earth's is another critical, yet often undetectable factor. This invisible shield protects a planet's atmosphere from being stripped away by the relentless solar wind, a stream of charged particles emanating from the star. Without a magnetic field, even a planet with a seemingly robust atmosphere could find its protective layer eroded over millions of years, leaving its surface exposed and inhospitable. This is a slow, insidious process, but one that is vital for long-term habitability. The existence and strength of a magnetic field are incredibly difficult to measure for exoplanets, making it a significant unknown in our assessments. The geological activity of a planet also plays a crucial role. Earth's plate tectonics, for instance, is a vital process that recycles nutrients, regulates atmospheric carbon dioxide levels, and drives geological diversity. This constant churning of the planet's crust is thought to be essential for maintaining a stable climate over geological timescales. Many exoplanets, even those that appear Earth-like in size, might be geologically inert, lacking the internal heat or structure to support such dynamic processes. This would mean a lack of nutrient cycling, a less regulated climate, and potentially a less diverse environment, all of which are detrimental to the emergence and sustenance of complex life. The chemical composition of the planet itself is another subtle but vital factor. While we can infer some elements from spectral analysis, the precise abundance and distribution of key elements necessary for life, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, CHNOPS, are incredibly hard to determine. Life as we know it is built upon these specific building blocks. An exoplanet might have water, it might have a suitable temperature, but if the fundamental chemical ingredients are not present in the right forms and quantities, life might simply never get a foothold. Even the type of star a planet orbits can introduce complexities. Red dwarf stars, for example, are incredibly common and often host planets within their habitable zones. However, these stars are also prone to powerful flares and intense radiation, which could be devastating to life on orbiting planets, especially those without strong magnetic fields or dense atmospheres. The stability of the star over billions of years is also a factor. Life needs time to evolve, and a star that undergoes extreme fluctuations could disrupt this process. So when we label an exoplanet as Earth-like, we are referring to a handful of observed characteristics, primarily size and orbital distance. We are, in essence, looking at a silhouette, a tantalizing hint of possibility. The deeper, intrinsic qualities, the atmospheric composition and pressure, the presence of a protective magnetic field, the dynamism of its geology, the precise elemental makeup, and the nature of its host star. These are the hidden ingredients, the subtle nuances that truly determine whether a world is capable of harboring life. The universe is a vast and complex laboratory, and the conditions that led to life on Earth appear to be a remarkably intricate and delicate confluence of factors, not easily replicated. And so, the seemingly familiar echo of an Earth-like exoplanet whispers of a profound truth, that our own world is not just a planet, but a rare and precious crucible, where countless, often imperceptible, conditions have converged to spark and sustain the vibrant tapestry of existence. The absence of life elsewhere highlights Earth's uniqueness. The sheer, overwhelming silence we encounter when we peer into the cosmos, even with our most advanced instruments, serves as a profound testament to the extraordinary nature of our own blue marble. For all the billions of stars and trillions of planets we believe exist, the evidence for life beyond Earth remains stubbornly elusive. This isn't a failure of imagination, but a reflection of the incredibly specific and delicate set of circumstances that allowed life to not just begin, but to flourish and evolve on our planet. Consider the challenges. A planet needing to orbit a stable star within a habitable zone, possessing liquid water, a protective atmosphere, a magnetic field to deflect harmful radiation, and a geological dynamism that recycles essential elements. Many exoplanets detected are super-Earths, larger than our own, suggesting potentially higher gravity and thicker atmospheres that might be crushing rather than life-supporting. Others are tidally locked, with one side perpetually scorched and the other frozen, creating extreme temperature gradients that life as we know it would struggle to endure. Then there are the gas giants, immense worlds of swirling clouds and crushing pressures, offering no solid surface for life to anchor itself. Even planets that appear superficially similar to Earth, orbiting in their star's habitable zone, may lack the crucial ingredients or possess unseen hazards. Perhaps they lack sufficient oxygen or have an atmosphere too rich in toxic gases. Maybe their star is too volatile, prone to frequent, life-sterilizing flares. The very composition of a planet's core, its mantle, and its crust plays a role. The presence and movement of tectonic plates, for instance, are vital for regulating climate and cycling nutrients over geological timescales. Without this slow, constant churning, a planet could become geologically stagnant, its atmosphere depleted of vital carbon dioxide, leading to a runaway ice age. The delicate dance of atmospheric gases, the precise composition of the oceans, the very frequency of asteroid impacts, all these factors, when combined in the right proportions, create the conditions for life. The fact that we observe this complex symphony playing out on Earth, and yet find no clear echoes elsewhere, suggests that the emergence and sustained evolution of life is not a guaranteed cosmic event, but a rare and precious occurrence. This absence, this cosmic quietude, doesn't diminish the wonder of the universe, but rather amplifies the miracle of our own existence. It transforms our home from just one planet among many into a unique, vibrant sanctuary, a testament to the improbable confluence of cosmic fortune. It is a powerful reminder that while the universe may be vast and full of potential, the actualization of life, as we understand it, is a remarkably delicate and perhaps singular achievement. The lack of definitive signals from other worlds compels us to look inward, to appreciate the intricate web of factors that make Earth so special, and to recognize the profound responsibility we have to protect this singular haven. It's as if the universe, in its immense scale, has presented us with a unique masterpiece, a living, breathing work of art that stands alone in the vast, silent gallery of space. This profound observation underscores not just the scientific rarity of our planet, but also a philosophical depth to our place within it. The quiet of the stars whispers a story of Earth's singular brilliance, a precious echo in the vast, silent expanse. Our planet is a fragile oasis in the cosmic desert. When we gaze out at the vast expanse of the cosmos, it's easy to be overwhelmed by its sheer scale and apparent emptiness. For every star, there are countless dark voids, regions where matter is so diffuse that it seems to stretch into infinity. This is the cosmic desert, a place of profound emptiness and extreme conditions. Our Earth, in contrast, is a vibrant, teeming sphere, a pocket of extraordinary complexity and delicate balance. It is a testament to a confluence of improbable circumstances that allowed life, as we know it, to take root and flourish. Consider the immense distances between stars. Even our nearest stellar neighbor, Proxima Centauri, is over 4 light-years away. This means that light, traveling at the universe's ultimate speed limit, takes 4 years to traverse that gap. The spaces between galaxies are even more staggering, often measured in millions or billions of light-years. These are not just empty spaces. They are regions where the fundamental forces of the universe operate with stark indifference to the existence of fragile life. Radiation from distant supernovae, cosmic rays accelerated to near light speed, and the relentless expansion of space itself are constant, pervasive forces in this desert. Yet here on Earth, we are shielded. Our atmosphere, a relatively thin veil, deflects much of the harmful radiation. Our planet's magnetic field, generated by the molten iron core, acts as a powerful shield, deflecting the solar wind, a stream of charged particles from the sun that would otherwise strip away our atmosphere over time. This magnetic shield is not a given. It requires a specific internal structure and dynamic within our planet, a dynamic that may be rare elsewhere. Furthermore, the presence of liquid water, so fundamental to life as we understand it, is itself a remarkable feature. Water requires a specific range of temperatures and pressures, conditions that are found within a narrow band around stars, the habitable zone. But even within this zone, a planet must possess the right atmospheric composition and pressure to maintain liquid water on its surface. Many planets in habitable zones are tidally locked, with one side perpetually facing their star, leading to extreme temperature differences, or they may have lost their atmospheres due to stellar activity or a lack of a protective magnetic field. The geological activity of our planet also plays a crucial role. Plate tectonics, the slow, continuous movement of Earth's crust, recycles essential nutrients, regulates atmospheric carbon dioxide through volcanic outgassing and weathering, and creates diverse environments that promote biodiversity. This dynamic geological engine is not a universal feature of rocky planets. Some may be geologically dead, their internal heat long dissipated, unable to sustain the processes that make Earth so dynamic. The very composition of our planet, the specific abundance of elements like carbon, hydrogen, oxygen, nitrogen, and phosphorus, is also critical. These elements, forged in the hearts of stars and dispersed through supernovae, had to come together in the right proportions to form the building blocks of life. Even the presence of a large moon, like our own, is thought to have played a stabilizing role in Earth's axial tilt, leading to more consistent seasons and a more stable climate over geological timescales. The absence of such a moon on many exoplanets could lead to chaotic climate shifts, making the sustained evolution of complex life far more challenging. The cosmic desert is a place of immense power and potential, but it is also a place of extreme challenges. Our planet, with its intricate web of interconnected systems, its atmosphere, magnetic field, hydrosphere, and geosphere, represents a delicate and perhaps rare equilibrium that has allowed life to thrive. It is a sanctuary, a precious anomaly in the vast, indifferent expanse. This singular speck of warmth and wonder is our only known home, a precious anomaly cradled within an immensity that barely notices its existence. Understanding other worlds deepens our appreciation for this one. As we venture in our minds across the silent, stardusted expanse, exploring the stark beauty and terrifying indifference of our neighboring planets, a profound shift begins to occur within us. Each barren landscape, each superheated atmosphere, each world locked in eternal ice, serves as a stark, yet gentle reminder. It is a reminder of the exquisite, almost improbable, conditions that allow for the symphony of life to play out here, on our own blue marble. When we contemplate the crushing pressures of Jupiter, or the barren, radiation-scorched surface of Mercury, we are not just learning about distant celestial bodies. We are, in essence, learning about the preciousness of our own existence. The sheer improbability of Earth's perfect cosmic alignment, its stable orbit, its protective magnetic field, its life-sustaining atmosphere, its abundant liquid water, becomes ever more apparent. These are not mere facts to be catalogued. They are the threads of a magnificent tapestry woven over billions of years that cradles us. To truly understand the challenges and limitations faced by other worlds is to gain a deeper, more intimate appreciation for the delicate balance that makes our home possible. It is to see the mundane miracle of a sunrise, the gentle caress of a breeze, the simple act of breathing, not as guarantees, but as extraordinary gifts. This journey through the cosmos, this contemplation of the alien and the inhospitable, ultimately leads us back to ourselves, to the singular wonder of being alive, here and now on this earth. It is a perspective that transcends the anxieties of the day, a reminder of the vast cosmic context within which our individual lives unfold. And in that unfolding, we find a quiet, profound sense of peace. The more we understand the universe's vast, often hostile nature, the more we recognize the extraordinary, serendipitous miracle that is our home. In the quiet contemplation of distant worlds, we find the most eloquent testament to the gentle miracle of our own. The loneliness of space underscores Earth's preciousness. Consider the sheer, immeasurable vacuum that separates celestial bodies, a vast, silent expanse where the echoes of existence are vanishingly faint. When we gaze out at the cosmos, we perceive not a bustling neighborhood, but an almost unfathomable emptiness punctuated by distant, solitary lights. This profound isolation, this cosmic solitude, serves not as a testament to our insignificance, but rather as a stark and beautiful reminder of the singular miracle that is our home. The distances between stars are not mere numbers. They are gulfs of time and space so immense that the very concept of crossing them strains our comprehension. Imagine a journey of thousands, even millions of light years. Light, the fastest thing we know, takes an eternity to traverse such voids. This means that for all practical purposes, the stars are isolated islands, each potentially harboring its own unique story, but separated by barriers that seem, to us, insurmountable. The absence of readily discernible, neighboring life within our immediate cosmic vicinity amplifies the preciousness of our own biosphere. While the universe is undoubtedly vast and likely teeming with possibilities, the sheer scale of the void makes the existence of a planet like Earth, with its complex, interconnected web of life, an event of extraordinary improbability. This is not to say that life cannot exist elsewhere, but rather that the conditions required for it to arise, to flourish, and to become detectable are so specific, and so finely tuned that our own world stands out as an exceptionally rare jewel. The silence of space, punctuated only by the faint whisper of cosmic microwave background radiation and the occasional surge of a distant supernova, is a powerful testament to the fragility and the unique nature of Earth's living systems. It is a silence that invites us to reflect not on our isolation, but on the remarkable gift of companionship we have found here with each other and with all the myriad forms of life that share this planet. The loneliness of the cosmos, in its stark reality, doesn't diminish us. It elevates the wonder of our own existence. It is a vast, silent canvas upon which the vibrant, dynamic, and intricate masterpiece of Earth's life is painted, making our shared existence all the more profound and cherished. The sheer scale of the void, the unfathomable distances, the seeming emptiness between worlds, all conspire to highlight the extraordinary nature of what has happened here, on this small, blue marble. Our planet is not just a place to live. It is a vibrant, singing anomaly in a universe that, for the most part, remains profoundly quiet. The vastness of space, in its silent grandeur, is the ultimate backdrop that makes the symphony of life on Earth resonate with unparalleled beauty and significance. It is in this profound quietude that we truly begin to understand the preciousness of our shared home, a beacon of life in an otherwise silent expanse. In the silent theater of the cosmos, Earth's vibrant song of life is a melody of immeasurable value. This moment of existence is a profound gift. As we draw the gentle threads of our exploration to a close, reflecting on the stark contrasts and unforgiving environments of our solar system's celestial neighbors, a profound truth begins to settle, like dust motes dancing in a quiescent beam of starlight. We have journeyed through infernos and ice worlds, through crushing pressures and suffocating atmospheres, each destination a stark testament to the extraordinary circumstances that allow life, as we know it, to flourish on this singular blue marble. It is easy in our daily lives to become accustomed to the quiet miracle of our own existence, to overlook the intricate tapestry of conditions that make our breath possible, our thoughts coherent, and our very being a vibrant, conscious experience. But when we step back, when we allow the vastness of space and the diversity of planetary forms to wash over us, the sheer improbability of our presence here becomes not a source of anxiety, but a wellspring of deep, abiding gratitude. Consider the delicate dance of our planet's orbit, a precise distance from our star that allows for liquid water, a substance so fundamental to life that its presence is often the first indicator we seek when searching for habitable worlds. This orbital sweet spot, this Goldilocks zone, is not a guarantee of life as we've seen, but its absence is almost certainly a disqualifier. Our Earth, however, holds this precious liquid in abundance, cradling it within oceans that teem with mysteries and sustain ecosystems of breathtaking complexity. Then there is our atmosphere, a protective blanket woven from a specific blend of gases, filtering out harmful radiation from the sun, moderating our temperatures, and providing the very air we inhale with each calming breath. Imagine a world without this gentle shield, bombarded by solar flares or choked by toxic fumes. Our Earth, in its atmospheric composition, offers a sanctuary. Think too of our planet's magnetic field, an invisible shield generated by the molten core, deflecting the relentless stream of charged particles from the sun that could otherwise strip away our atmosphere, rendering the surface sterile and inhospitable. This unseen guardian, this silent protector, is a testament to the dynamic geological processes that have shaped our planet over eons, processes that are themselves a delicate balance of heat, pressure, and chemical reactions. The very stability that allows for the slow, incremental evolution of life is a product of these ongoing, yet remarkably consistent terrestrial forces. The presence of a large moon, stabilizing our axial tilt and creating the ebb and flow of tides, has also played a crucial, often underestimated, role in shaping our planet's climate and fostering the conditions conducive to life's emergence and diversification. The cyclical nature of day and night, the predictable progression of seasons, these rhythms, so deeply ingrained in our experience, are themselves part of a grander cosmic choreography that supports our existence. Even the seemingly random distribution of elements, the precise elemental makeup of our planet's crust and mantle, the availability of carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur in forms that can be readily utilized by biological processes. These are not accidents, but rather the outcome of stellar evolution and the grand cosmic recycling of matter that has occurred over billions of years. The formation of our solar system, the accretion of dust and gas into planets, the specific sequence of events that led to Earth occupying its unique position, all of this points to a confluence of factors that is, statistically speaking, remarkably rare. When we consider the sheer number of stars in our galaxy alone, let alone the trillions of galaxies in the observable universe, and then contemplate the precise conditions required for life to arise and persist, the preciousness of our own existence becomes undeniably clear. It is not a matter of arrogance to recognize this uniqueness, but rather a profound acknowledgement of the extraordinary journey that has led to this very moment, to this consciousness, to this ability to ponder the cosmos. Each breath we take, each thought we form, each sensation we experience is a direct consequence of this improbable confluence of cosmic and terrestrial events. The challenges we face, the anxieties that may arise, can often feel overwhelming, but when viewed through the lens of our planet's miraculous journey, they can also be seen as part of the rich, complex tapestry of a life that is, in itself, an improbable and invaluable gift. In the quiet hum of existence, This fragile, vibrant moment is a whispered echo of cosmic chance, a rare bloom in the vast, silent garden of the universe, and therefore a treasure beyond measure. Our calm exploration has covered the stark realities of our solar system and the vast, often inhospitable, expanse beyond. We've journeyed through the fiery embrace of Venus, the frozen desolation of Mars, and the crushing depths of the gas giants. We've touched upon the delicate balance of atmospheric pressure, the protective shield of magnetic fields, and the vital role of water, all while acknowledging the profound complexities that lie beyond simple observation. Tonight, we have reviewed the principles that make our Earth a truly miraculous anomaly, a rare haven in a universe that often seems indifferent to the very concept of life. The sheer improbability of our existence, the intricate dance of cosmic forces that have conspired to create this vibrant, breathing planet, should not be a cause for anxiety, but rather a profound source of wonder. Consider, for a moment, the immense journey of light from distant stars that has traveled for eons to reach us, the silent witness to the unfolding of galaxies. In the grand tapestry of the cosmos, our small blue marble, teeming with life, is an extraordinary, precious jewel. The very challenges and harshness of other worlds serve to illuminate the quiet miracle that is our own. You are not just living on a planet. You are existing within a symphony of cosmic events, a rare and beautiful performance. This understanding, this quiet awe, can help to dissolve the anxieties that tether you to wakefulness. It is time to rest now. Allow the vastness we have explored to lull you into a state of deep peace. Release the day and embrace the profound comfort of knowing you are part of something so grand, so improbable, and so utterly beautiful. Sleep well. Good night. It is time to rest now. If you happen to still be awake, you can drift into the next chapter now, continuing your journey through the quiet wonders of the universe.